Okay, great. Thanks a lot. Yeah, so thanks for the invitation. I hope I can complete the talk. My internet works. All right, yeah, so I'm going to be talking about some exponential mixing results obtained with Alex Blumenthal and Sam Punshon-Smith. Okay, so I'm going to start from not talking about mixing for a few minutes, but first just talk about turbulent systems in general. So many of them are well approximated by statistical stationary systems. So for example, imagine wind over a sail or water over a stone. The issue with modeling this is that for deterministic systems, the construction of the invariant measures that would model this kind of behavior is really hard. I mean, we're not even close to being able to do this. It requires too deep of an understanding, and we're not even close. So that's one of the motivations for moving to random systems, because there at least you have this, as we'll see, you have this to stand on. So for example, oops. Well, okay, I guess some of my blue marking is still here from when I gave this talk last. Right, so for example, the stochastic Navier-Stokes equations, you want to study with stochastic forcing, so you put in some white in time forcing. It doesn't really have to be white in time per se, but let's. And then what you want to do is you want to take time to infinity and then send nu to 0. So this would be understanding, for example, the 3D Navier-Stokes equations in a statistical stationary regime. We're not even close to being able to do that. There's actually essentially nothing rigorous known about this kind of ordering limits. So when you study turbulent systems, you say, okay, well, in the statistical stationary case, it's basically nothing, and it's not clear what kind of techniques we have that could make even the smallest dent in this problem. So the idea is, all right, are there much simpler problems that we can think about that have some flavoring of this? So we found a problem. It's a specific subcase of passive scalar turbulence. So what you do is you solve the Navier-Stokes equations, or maybe some other fluid equation. It's maybe some other fluid equation. But here I'm going to fix the Reynolds number. So this parameter is going to be fixed. It doesn't need to be small or large, but I just don't want to send it to 0. Then I'm going to solve this passive scalar equation also with a stochastic source to 0. And what I want to understand is the statistics of this scalar g. So think of this as like a salinity variation or something like that in your fluid. But your fluid is kind of at an order 1 Reynolds number. So to fix ideas, let me just talk about the 2D Navier-Stokes case. In 3D, we have to use hyperviscosity. But other than that, it's similar. For reasons I'm not going to be able to get into in such a short talk, we use a non-degeneracy condition at least at high frequencies in the forcing. So this means that the forcing has to be active at all modes, but it can't be too rough, because then otherwise you mess up all the turbulence. So this parameter alpha, think of it as like a million, something like that. So the velocity fields are pretty regular, and it's not hard to prove that the stochastic Navier-Stokes equations are globally well posed in some Sobolev space associated to alpha. Yeah, okay, I've got all this blue marking on that slide. It's well known. There's beautiful works by Flenderly and Maslowski and Heyer and Mattingly. It's well known that under actually much more general conditions, at least on the torus anyway, that there's a unique stationary measure for this problem. So that means that if you randomize the initial condition with respect to this measure, then the statistics of observables don't change. So phi is some function on phase space. Think of it as like a measurement that you would make of the system. And the expected value of that observable is stationary in time. And you can show that actually because uniqueness of this measure, the long-time averages of all the observed parameter limit in a singular limit. So sort of the statistical stationary turbulence problems are about one major aspect, at least, or maybe the most major aspect, is about studying this measure as the small parameter goes to 0. So we're going to study this measure when kappa goes to 0. Distribute themselves in phase space. So we found, well, okay, so what is normally found is that the conserved quantities form power laws in space. So here, you might consider the energy of the fluid, the scalar density of the scalar, the L2 density of the scalar. Yeah. Okay, so here's a sort of cartoon of what's observed and what. And so here the scale with the forcing act. So this is this is frequency, and this is law of the as a function of frequency. So here with the scale with the forcing acts, there's of course no universal theory for that. There's just whatever it is, what it is. Then there's this scale where the fluid is turbulent, and there's some prediction, passive scalar turbulence, that says the power spectra should match actually. But then if you go further, the dissipative cutoff of the fluid is at some scale. And beyond that, where the fluid looks smooth, then the scalar does not look smooth if kappa is small enough. Then you see a -1 power spectrum. So this is called the Batchelor power law, the Batchelor power spectrum. So we have no idea about any of this. We don't know where this line is, of course, because we don't know anything when nu is going to 0. But this is what we're going to be able to prove rigorously. Okay, so this is what we're going to prove. Okay, so this has been observed many times. This cartoon picture. This is the same picture, but in actual observations in the ocean, in laboratory experiments, and in computers. In fact, it's actually important to emphasize Batchelor's law has nothing to do with hydrodynamic turbulence. It's almost the opposite. So if the fluid is turbulent at that scale in which the fluid does not look turbulent. And so what's going on? Okay, so one model that we could think of was based on the Arnold-Cat map. Trying to erase this. Based on the Arnold-Cat map. So you take a map of the torus that just multiplies by this matrix, and then wraps it back to the torus. And it's well known that it's extremely chaotic, and it's kind of uniformly mixing. So yeah, this is annoying. Right, so now the toy problem for this scalar turbulence is going to be every time step, we're going to just dump a random amount of scalar at a unit frequency, and then map the scalar field forward by the iterated cat map. And so because the cat map maps Fourier modes to Fourier modes, you can solve this explicitly, and you get this random Fourier series. And because the matrix is hyperbolic, and the eigenspaces line up correctly, this is growing exponentially. And you can show that in lambda-adic frequency shells, where lambda is an eigenvalue of the matrix, you get about order 1 energy. And that matches exactly Batchelor's law if you integrate over frequency shells. And so this is a toy model for Batchelor's law. And the key property that you see here that really gives rise to Batchelor's law is the exponential transfer from low frequencies to high frequencies. So you can imagine, if we're talking about an actual fluid now, so we've seen many times in this conference already, this is actually the notion of exponential mixing. So what we want to be able to prove somehow is that the Navier-Stokes equations or stochastic fluid equations or whatever are exponential mixers. And if you have suitable control on this, on the exponential mixing property, then you should be able to prove Batchelor's law. And that is the strategy. So what you can prove eventually, once you have that, is a Batchelor's law on the cumulative power spectrum. So this is the final statement of Batchelor's law of what we have right now. Which says, all right, if you fix nu, then there is a scale beyond which you see the Batchelor's law in the cumulative power spectrum. So you integrate -1 and you get a log. So that's what that means. Of course, you see this all the way until kappa to the -1/2, where the dissipation finally dominates. There's a bunch of other things that you can pass to the cap equals 0 and do some other singular things, but the important thing is Batchelor's law. So let's talk about the exponential mixing aspect, because I think that's maybe even more interesting for this conference. The fundamental building block is, of course, the Lagrangian flow map of the fluid. So this tells you, given a particle, where does it go in the fluid? So it's just a solution to this random ODE. And at least if kappa is equal to 0, all the dynamics of the scalar are determined by this flow map. And so what we want to get at, I guess right here essentially, which is, as I said before, what we really want to get at is this notion of mixing. And we're going to quantify mixing with the H-1 norm. Well, any negative sublevel norm will work. As we've seen in other talks, this basically says, okay, at least if your L2 norm is conserved, if your H-1 norm goes to 0, then the information has to be shifting from low frequency. And as Andre talked about yesterday, you can't get H-1 decay if you don't somehow pay regularity. So whenever you get a negative sublevel space, you should get a positive sublevel space. This is just from, and when understanding correlation decay, if you define this to be your some kind of measure of correlations in the Lagrangian flow map, So you can connect these two by the duality formulation of the HS form. And so the main result that we actually proved, and once you have it, let me get rid of this marking. Once you have it, is the proof of Batchelor's law is not so bad. Is this almost sure exponential mixing? So what it says that for all values of nu and for all parameters p, and I'll explain this p, there's a deterministic mixing rate gamma that is independent of kappa, such that all passive scale, so all scalars, everything's average 0, of course. All scalars in H1 mix exponentially with the same exponential rate, but with a random constant that depends on the initial condition of the velocity field, and it depends on the entire noise path, so the entire path of the.
Great. So as Jacob observed, this theorem regarding H-1 decay has to do with the passive scalar equations subjected to advection by stochastic Navier-Stokes or any one of these fluid models in the presence of kappa strength diffusivity, but in the absence of random forcing is maybe something Jacob didn't mention. Right. Okay. What else do we want to say? We want to say that this almost sure exponential mixing rate, this exponential mixing rate itself is optimal for stationary fluid motion or for fluid motion coming from a fixed velocity field when kappa equals 0. You really don't expect to do better than exponentially fast. This really just has to do with the fact that the advecting fluids themselves are uniformly Lipschitz, essentially, uniformly. Although in our case, stochastic fluctuations in the Navier-Stokes equations could lead to spikes in Sobolev norms. This is still true, though, that statistically stationary fluids that are Lipschitz regular, you do expect the optimal rate to be exponential. I should also, as a kind of a side note, these are, to our awareness, the only examples of uniform and kappa exponential mixers. At this point, even among uniformly hyperbolic flows, this doesn't appear to be known yet. It is also possible using the methods in our proof to construct CK and time exponential mixers as well. So we can do a little bit better than White and time, but we're no longer working with solutions to the stochastic Navier-Stokes equations. At any rate, several of the attendants of this conference have already very similar work. So proving a result like this, or I should say that sort of a near immediate consequence of this is L2 enhanced dissipation. In comparison with the e to the negative kappa t decay rate that you expect from the heat equation, we actually get exponential in time mixing with a kappa -1 out front, where d is the same random constant appearing there, right? So really, the fluid advection is generating so many small scales that the dissipation really eats up, and this results in in a much faster exponential rate. I would also note that this exponential. Can everyone see my highlight?
Yes.
Okay. I would also note that this exponential rate with the kappa inverse out front is essentially saying that by time absolute value log kappa, you see the L2 norm halve, basically go in half. So absolute log kappa is essentially the time scale at which this mixing is occurring. And as we also note in this paper, this time scale is essentially optimal among regular fluids, non-turbulent fluids. Great. So the proof itself is a combination of a variety of techniques coming from random dynamical systems and stochastic PDE. How long do I go until?
You have about 5 more minutes. About 5 more minutes.
5 more minutes. Okay, got it. So
yeah, Alex, I was going to skip Furstenberg.
Oh, okay. Cool.
Yeah.
All right. So at any rate, the point of this so-called Furstenberg stuff is essentially tools from random dynamical systems theory to establish that the actual Lagrangian flow is chaotic in the sense that nearby initial conditions separate fast. And this in dynamical systems theory is used to prove mixing estimates. So it's kind of a lemma on the way to establishing almost sure exponential mixing, or almost sure H-1 decay. And the key to this in our analysis is the following sort of Chebyshev L2 trick, if you like, is that the probability that this the time n scalar paired with some g has a value greater than some exponentially decaying thing. Well, by Chebyshev, this can be bounded from above by this. All right. Where here, notice that we've squared the left and the right hand sides in order to apply Chebyshev. And when you have these two, when you have the square of this integral, you can basically treat both instances of the integral as separate dummy variables and recombine them and take this exponential inside. And so what pops up is this 2-point motion, okay, where I'm now tracking the separate motions of a pair of passive tracer particles being advected by the same fluid subjected to the same noise, okay? And so if you kind of stare at this thing, you realize, well, this has to do with the rate at which this 2-point motion equilibrates to its stationary statistics, namely the stationary measure for the velocity field times Lebesgue. Unfortunately, though, we've traded one problem for another, that the diagonal, the set of trajectories where the two particles start on the same point, is invariant. And so we effectively need to treat this diagonal subset as part of infinity in order to establish a mixing estimate. And so necessarily any kind of mixing estimate that we would obtain, you would expect this function, this constant out front mat script v, to blow up as you take x naught and y naught close together. The main difficulty of this game, really, you want to keep the Markov chain out of bad parts of phase space, right? And that's the purpose of the drift function, mathcal v. Okay, a drift condition of this kind would ensure that the dynamics of the 2-point process utxt yt stays a bounded distance away from the diagonal, as long as this function is bounded away from the diagonal. Okay, right. So So somehow this drift function is encoding how trajectories are repelled from the diagonal, and this is where Lagrangian chaos comes in, the geometric separation of nearby initial conditions by the Lagrangian dynamics. When two particles are extremely close to the diagonal, which is to say that their distance is very small, we expect the difference between them, xt minus yt, to evolve roughly according to the gradient dynamics. This is just your favorite Calc 1 lemma. Of course, if dx phi t is growing at an exponentially fast rate, which is what we proved in Lagrangian chaos, then this is repelling. This is a source of strong repulsion from the diagonal. Okay. And so it's very natural to look for, in light of this sort of linearized analysis near the diagonal, it's very natural to look for a Lyapunov or a drift function of the form with an inverse power of dxy, right? So this is blowing up near the diagonal, remaining bounded away from the diagonal, in addition to some sort of corrector function, which we call psi p, which depends on u, x, and the orientation of the difference between the particles x and y. This cutoff function here is meant to be so that you only see this term very close to the diagonal. So this actually makes sense, right? So this is a cutoff that kills distance values larger than 1/10 or something, right? The construction of this psi p here follows from kind of sort of a now standard technique in large deviations theory called the Feynman-Katz or so-called twisted semigroup approach. Okay, which involves looking at the building off of the Markov chain tracking the velocity field, a particle position, and actually a tangent vector at this xt. So you can think of this as approximating the linearized dynamics near the diagonal. So on its own, without this extra term, this would just be the Markov semigroup governing this UTXT directional VT process, right? But we are throwing in this extra term here to study the large deviations theory of this dx phi tv. Okay, the rate at which this Lyapunov exponent is realized. I see that I'm roughly out of time. The punchline of this is that this Markov operator admits a dominant eigenvalue, negative lambda p, and this lambda p is essentially going to feed back into our drift estimate. So I think that I'll skip forward a little bit. Okay. So to kind of just wrap up, I promise I'll take no longer than 30 seconds. Random dynamical systems is really fantastic and opens up a wide variety of possibilities for rigorous proofs of universal turbulence laws. On the other hand, passive scalar turbulence is way easier than actual legitimate hydrodynamic turbulence or wave turbulence, other turbulent systems. And so really, to some extent, we got lucky. Another shortcoming of this method is that the techniques we use to prove the almost sure mixing rate and the Lagrangian exponent are just somehow soft. They're not quantitative. And so I can't actually tell you the dependence of any of these mixing rates on, for example, the Reynolds number of the underlying fluid. That being said, we are working on this, and this is a subject of future work. This is just a brief description of future work we're into, but I think I'm totally out of time now. So thank you very much for your attention, and I'm sorry for Jacob's bad internet.